Now that we know how a signal can spread through a neuron through an electrotonic potential and action potentials and combinations of the two, let's put it all together by looking again at the structure of a neuron, the anatomy of a neuron, and thinking about why it has that anatomy and how it all can work. So we've already talked about the dendrites as being where the neuron can be stimulated from multiple inputs. If we're in the brain, these dendrites might be near the terminal ends of axons of other neurons. If we're some type of sensory cell, these dendrites could be stimulated by some type of sensory input. But let's just say, for the sake of argument, they are stimulated in some way. And because they're stimulated in some way, it allows positive ions to flood in. It allows positive ions to flood in to the neuron from the outside. As we know, there's a potential difference. It's more negative in the neuron inside of the neuron than outside of the neuron. And so if a channel gets opened up because of some stimulus, that would allow positive ions to flow in. And the primary positive ions we've been talking about are the sodium ions. Maybe this is some type of sodium gate that gets opened up because of this stimulus. So when that happens, you will have electrotonic spread. You will have an electrotonic potential being spread. So let's say that we had a voltmeter right here on the axon hillock. It's kind of the hill that leads to the axon right over here. So what you might see happening after some amount of time, so let me draw. So let's say this is our voltage in millivolts across the membrane, our voltage difference, I should say. This is the passage of time. Let's say the stimulus happens at time 0, but right at time 0, we haven't really noticed it with our voltmeter. Our voltage right across the membrane right over there is at that equilibrium, negative 70 millivolts. But after some small amount of time, this electrotonic potential has gotten to this point because all of these positive charges are trying to get away from each other. And it's gotten to that point, and you might see a bump in the voltage, in the voltage difference, I guess I should say. This thing might go up. So it might look something like that. Now that by itself might not be, we might not have gotten the voltage difference low enough, I guess we could say, or we might not have gotten the voltage inside of the membrane, inside the cell, positive enough in order to trigger the voltage-gated ion channels. And so maybe nothing happens. Maybe this right over here, this is negative 55 millivolts. And so that's what you have to get the voltage up to, the voltage difference up to, in order to trigger the ion channels right over there. So those are the sodium channels to get positive charge in. Here's the potassium channels to get the positive charge out. The axon hillock has a ton of these because these are really there. Once they get triggered, they can trigger an impulse that can then go down the entire axon and maybe stimulate other things, maybe in the brain or whatever else this neuron might be connected to. So maybe that stimulus by itself didn't trigger it, but let's say that there's another stimulus that happens right at the same time or around the same time, and that happens, and on its own, that might have caused a similar type of bump right over here. But when you add the two together and they're happening at the same time, their combined bumps are enough to trigger an action potential in the hillock, or a series of action potentials in the hillock. And so then you really have essentially fired the neuron. So now all sorts of positive charge gets flushed into the neuron, and then purely through electrotonic spread, you will have this electrotonic potential spread down the axon. Now this is the interesting part, because we can think a little bit about what is the best way for an axon to be designed. In general, if you're trying to transfer a current, the ideal thing to do is the thing that you're transferring the current down should conduct really well, and you could say it has low resistance, but you want it to be surrounded by an insulator. You want it to be surrounded, so if this was a cross section, you want it to be surrounded by an insulator that has high resistance. And the reason is because you don't want the potential to you don't want the potential to leak across your membrane. High resistance right over here. If you didn't have something high resistance around it, then your signal will actually your current would actually go slower. This is true if you're just dealing with electronics. If you just had a bunch of copper wires on one side and you had some copper wires that were surrounded by a really good insulator, a really good resistor, for example, plastic or rubber of some kind, the current is actually going to have less energy loss. It's going to travel faster when it's surrounded by an insulator. So you might say, okay, well, gee, the best thing to do would be to surround this entire axon with a good insulator. And for the most part, that is true. It is surrounded by a good insulator. That is what the myelin sheath is. So let's say we wanted to surround this whole thing with just one big grouping of Schwann cells. So one big myelin sheath, which is a good insulator. It does not conduct current well. So this right over here is just one big myelin sheath. One big myelin sheath right over here. Now what's the problem with this? Well, if this axon is really long, and let's say you're a dinosaur or something, and you're trying to go up your neck, and your neck is 20 feet long, or even a human being, where we're of reasonable size, and you're going several feet, or even whatever, you want to go a reasonable distance, purely with electrotonic spread, your signal, remember, it dissipates. Your signal is going to be really weak right over here. You're going to have a weak signal on the other end. It might not be even strong enough to make anything interesting happening at these terminals, which wouldn't be strong enough to trigger maybe other neurons or whatever else might need to happen at this other end. So then you say, okay, well, then why don't we try to boost the signal? Well, how would you boost the signal? Well, you say, okay, I like having this myelin sheath, but why don't we put gaps in the myelin sheath every so often, and then those gaps would allow the membrane to interface with the outside, and in those areas we could put some voltage-gated channels that can release action potentials in order to essentially boost the signal. And that's exactly what the anatomy of a typical neuron is like. So instead of just one big insulating sheath like this, it would, let me make some gaps here. Whoops, I wanted to do that in black. So actually, let me just draw it like this. Let me just erase this. So clear, and let me clear this. That's good enough. And so what we could do is we could put gaps. We could put gaps in it right over here where the axonal membrane itself can interface with its surroundings. And of course, we know we call those gaps the nodes of Ranvier or Ranvier. I'm not really sure how to pronounce it. So let me put those gaps in here. So you put those gaps in here. So these are the myelin sheath. And this right over here is a node of Ranvier. These are nodes of Ranvier or Ranvier. And right in those little nodes, right where the myelin sheath isn't, we can put these voltage-gated channels. We could put these voltage-gated channels to essentially boost the signal. If the signal had to go electrotonically all the way over here, it'd be very weak. It's going to dissipate as it goes down, but it could be just strong enough right at this point in order to trigger these voltage-gated channels, in order to essentially boost the signal again, in order to trigger an action potential, boost the signal, and now the signal is boosted, it'll dissipate, boost, and it'll boost right over here again. And then it'll dissipate, and boost. Dissipate, boost. And so by having this combination, you want the myelin sheath, you want the insulator in order to keep the transmission of the current to fast, in order to have minimal energy loss. But you do need these areas where the myelin sheath isn't in order to boost the signal, in order for the action potentials to get triggered, and so your signal can keep being amplified, if we wanted to talk in kind of electrical engineering speak. And this type of conduction, where the signal just keeps boosting, and if you were to just kind of superficially observe it, it looks like the signal is almost jumping. It gets triggered here, then it gets triggered here, then it gets triggered here, then it gets triggered here, and then it gets triggered here. This is called saltatory conduction. Saltatory conduction. Saltatory conduction. And it comes from the Latin word saltare, or once again, I don't know how to pronounce, my Latin isn't too good, but it comes from the Latin word for saltare, which means to jump around or to hop around. And that's because it looks like the signal is hopping around. But that's not exactly what's happening. The signal is traveling passively through, it gets triggered here in the axon hillock, then it travels passively through electrotonic spread, and then it gets boosted, and you have the myelin sheath around it to make sure it goes as fast as possible, and you get very little loss of signal. And then it gets boosted at the nodes of Ranvier because it triggers these voltage-gated channels again that triggers an action potential, and then your signal gets boosted, and then it dissipates, boosted, dissipates, boosted, dissipates, boosted, dissipates. Maybe it could even get boosted again, and then it can trigger whatever else it has to trigger.